the recording, you need to record it yourself. Thank you very much.
Yeah, okay. Lesson with some short polls just to check your attention during last Monday. So here we are. So we will start with some poll. So basically you need a browser or your smartphone as you prefer, and go to the URL listed here, www.menti.com, and when prompt, use the code 3257663. So I repeat, please go to the following page, www.menti.com, and when prompted, use the following code. So there is a question about last lecture, and the question is on definition of primary energy, and you have three options. So of course you see here we have the number of participants to the poll. So I will leave you time for answering a few minutes until we reach, let's say, 30 participants. So I see that you have provided the right answer. So you are quite careful during last lesson. So I will move to the next poll, which is once again questions with three different options. And the question is the following: what is the ratio between energy consumption in 2019 and 1800? And you have, once again, three different options. And here you're not influenced by your colleagues because you don't see what your colleagues are answering. But we see that the counter is increasing, so already 9 people have answered. And as before, I will wait until about 30 people would answer. So nobody else is answering. So we will stop the poll here and check the answers. So here, more diverse set of answers, and the right answer is the first one. So it was 30, about 30.7, the ratio between the energy consumed in 2019 and 1800, not more. So thanks for the poll, and just to briefly review the contents of previous lecture, and then of course we will move to new topics. So you might remember we were discussing about the total primary energy supply per capita in the world. These are data in with reference to 2016, and we are seeing here a very heterogeneous situation. So there are a lot of diverse situations in the different country, which is one of the main problems. If you think about it, one of the main problems is that things are so different in the different countries, and so a common solution is not easy to find. So we'll delve into this data to show you pitfall and fallacies. So once again, we will delve into detail of primary energy. And so this is the trend of primary energy in the last year. So you see here, these are the trends starting from 1993 to 2018. And these are, once again, energy consumption in the world in TOE. So million of tons of equivalent oil. And once again, you see here different colors from different sources. So green is oil, red is natural gas, yellow is nuclear, blue is hydroelectric, and orange is renewable, and gray is coal. And you see that the trend, unfortunately, is that consumption is increasing, and also fossil fuel are increasing, especially because of natural gas, and slightly increase in oil, and quite important increase in coal. So the case study means, but let's look at single countries. So at first, of course, we are looking at Italy, and you see that for Italy, once again, numbers are in million of tons of equivalent oil. In the last 10 years, you see that there is a trend of decrease, but not so clear, because we have some kind of wave in the amount of total primary energy, which is the dotted line. And of course, components are showing us that oil is the first component still, and it has just been reached by natural gas. And of course, renewable, the dark green line, is increasing, has increased, but still quite negligible with respect to the other components. And so the case study looks at specific country. So after Italy, we are looking at Pakistan, which is a complete different country in terms of economics and social aspects. And you see that in Pakistan, the primary energy consumption has increased quite a lot, starting from 67 about to 85, million of ton of equivalent oil. And here you see that renewables are really negligible. Though for climate conditions, Pakistan would be quite suited to the use of solar energy. But still, this kind of technologies is not yet used in Pakistan, where you see that natural gas and oil are taking the lead, and they are basically exchanging each other. So you see that in last years, there was an increase in natural gas that was almost all equivalent to the decrease in oil. But still, oil and natural gas are 3/4 of the total energy consumption. Another case study is on Germany. And like for Italy, you see that numbers are quite constant with a trend of slight increase here, while for Italy was a slight decrease. But once again, you see that oil is the most important component for energy in Germany. And you see that there are major differences with Italy. The first difference is on coal. Germany has some internal production for coal, so they are using quite a lot of coal, which is bad because coal has a very high intensity of emissions. And we see that renewable have had a large increase from about 20 to 50 million of ton of equivalent oil per year, but still is less than half of oil alone. So these are different pictures from different country, and next country will be USA. So when it comes to USA, you see numbers are in overall picture quite equivalent to Italy and Germany. So Western country have a similar trend. So you see almost constant consumption in the last 10 years with some kind of waves. And once again, numbers are quite similar to Germany, but maybe this will be quite impressive for you. Unless the storytelling is saying that Germany is performing well and USA is performing bad, numbers are saying exactly the opposite. So you see that in the USA, the consumption of coal has almost halved. So despite the storytelling that Trump was boosting coal, numbers says the opposite, which is always important. So storytelling and news are one thing, but as technician, as expert, as paying attention to real data are saying the real things. And real thing is that coal is decreasing, while in Germany, it's increasing, which is quite nice. At the same time, you see here that similarly to Italy and Germany, oil and gas are taking the lead, even here, and renewable have increased, but less than in Germany. But still, in all the Western countries, renewable are still residual part of the overall share. And in Pakistan, they are pretty much negligible. So in conclusion, what we can say? In conclusion, we can say that apparently Pakistan is performing very bad, because in Pakistan, we have an increase of energy consumption, which is quite large. And in Western country, with some differences, we have pretty much constant trend. However, this analysis is wrong, because basically looking at the 4 countries, what you see is that the overall contribution of Pakistan is very small, though the number of inhabitants in Pakistan is very high. So what I'm saying, absolute numbers can provide you fallacies, because what is important is the consumption per capita, which is exactly the benchmark on how a specific country is impacting on energy and on environment. So this is just to say a specific comparison between Italy and Germany, showing that pretty much the same behavior, even if in Italy, top chart, there is a slight reduction, while in Germany, things are pretty constant with some waves. But most important is this picture. So basically, you might think Pakistan is performing bad, but here are the real numbers. So this picture shows that the energy used by one person in USA is equivalent to the energy used by many other in Pakistan. So in Pakistan, each person is using 0.425 tons of equivalent oil per capita. In the USA, 7. So of course, this is leading to more than 16. So more than 16 people in Pakistan are required to use the same energy of one person in the USA. And also in comparison between Italy and USA, the comparison is very strong, because 2 and more than half people in Italy are required to use the same energy one people in the USA does. And you see the same for Germany, which is almost half of the USA. So basically, this is the real picture. So in order to assess the use of energy and the impact on the environment of the different country, you shall use information per capita. Any other data is misleading, because of course, what has happened in Pakistan in the last 10 years? What has happened is that starting from very low use of energy per person, which is probably below the necessity, wealth is increasing, and so energy consumption is increasing. But the real question is it better to keep the consumption constant at 7 tons of equivalent oil per capita, or is it worse to move from 0.4 to 0.7? Yeah, so apparently doubling the consumption in Pakistan is not as bad as keeping constant the consumption in the USA. This is the real information we have from this data, and not from this data that are very misleading. So in conclusion, when you see this chart, you say, okay, this is the primary energy in the world. This is the same chart we had here. So of course, we see a constant increase of energy consumption in the last years in the world. But when you look at this chart, you think that the main responsible for the increase are non-OECD countries. So basically, OECD countries are USA, Europe, Australia, Canada, Western and rich countries. And non-OECD countries are lower income countries, but also Brazil, China, India. So looking at this chart, you might think that the main responsible for the increase of impact that is relevant, because we are basically seeing that more than 50% of increase of energy consumption in the last 15 years or so, which is a huge amount of consumption, and also related to that is a corresponding amount in emissions. So a very bad situation. You might think, okay, but Western countries are performing well because they are basically keeping constant their consumption or even reducing it. And at the same time, non-OECD countries have almost doubled their consumption, starting from about 4,000 to 8,000. But this is not the truth, because as we have seen before for the Pakistan case study, the situation is exactly the opposite. Countries in the red line are just increasing their level of consumption to a basic level, starting from very tiny, and the other country are using a lot of energy per capita, and they are keeping this consumption very high. So when you look at the same data in terms of per capita, you see things very differently. So you see that in North America, they have started from, North America is not only USA, so it's an average, and you have started from 6 tons of equivalent oil per inhabitant in 86, 85 year. And this level, 85, is quite far in time. And this level is almost constant. So basically was very high and is still the same. At the other hand, you have other countries. So for instance, this is Africa. The yellow is Asia. So of course, China is here, but still the increase is huge and more than doubling, but still not as a reference to USA or North America, is still 1/3. And at the same time, you see this is Europe, and still, yes, it's decreasing, but not so strong decreasing. What is really relevant is CIS, which is Russia, where you see the effect of economic crisis and other events that have led to some decrease, starting from 85 with a level close to North America, to now with a level close to Middle East and about Europe. So once again, beware of data, because they can be very misleading. So this is not the right way to look at data. This is the right way to look at data. And what is the bottom line here? The bottom line here is, but what is the level? So what is enough for wealthy countries? Is 2, is 3, is 1? This is the very important question. So we are about 2.5, and we are a very wealthy country. So why go at 6? This is first question. And even 2.5 is not too much. So the real question for the world now is, what is the level? And I would place this question in another point of view, from another point of view. So probably we should think of the level that is sustainable. So the real question is, what level of consumption is sustainable, where sustainable means that can be sustained for many generations from now on, because 6 tons of equivalent oil per capita is not sustainable, because we all know that the amount of fossil fuel we use there will not be available for 2-3 next generation, for the next generations. So we must place a very, very specific question. What is sustainable? And then all agree and find pathway to reach that level. This is the real analysis we should do, and that we will try to do from now on. Okay? And this is the final picture. So here you see what is the real situation in the world, from countries like North America with very dark red, meaning very high energy consumption, and per capita, so here data are per capita, and countries that are almost white, like in Middle Africa or somewhere in Asia. So that's the real picture, meaning that, I repeat, one of the hardest things to overcome is these differences, because of course it's very hard to find a common recipe, because everybody is starting from very different point of view and everybody has different problem. So I repeat, in Pakistan, their problem is to reach a level of enough wealth for surviving. On the other hand, in North America, the problem is to decrease the level of wealth, which is far beyond what is necessary. So, you know, since we have to find a common rule, because we are a common spaceship, common Earth, we have to fight a lot to find a single recipe, which is one of the hardest problems. So this concludes the part of energy balance, and I'm moving quickly to the next section. The next section would be very, very quick, because you have already had a number of lectures that have shown how climate and energy are very strongly related. And specifically, in 2015, there was a meeting that you probably know that is called COP in Paris. And in Paris, COP21 in 2015 was a milestone in the history of humanity, because in that meeting, it was the statement was very clear. Climate and energy are a problem for humanity, and we have to fight it. And basically, the conclusion of this meeting was that climate change is anthropogenic, and that the data you have seen in previous presentations are very clear and very scary. So we have to take action, as the title of this course is saying. So which action should be implemented by the different countries? This is not a trivial question. So first action is on energy, because energy in Europe is contributing to more than 80%. So these are data from European Union saying that more than 80%, sorry for the Italian, is of greenhouse gas emissions is coming from energy. All the other parts are negligible and are waste, agriculture, and industry. So all the other parts are quite negligible. The three of them is less than 20%. And so energy is the main problem to solve. So how to keep similar or probably reduced level of energy consumption with no greenhouse gas emissions. In the right chart, you see the same numbers. So emissions from 1970 to 2010. And once again, different colors are different components of emissions. And once again, the conclusion is the same as the left chart, the left pie. So more than 80% is coming from energy distribution and use. That is what we have discussed last Monday. And this chart on the right is also saying you another important information. So greenhouse gas emissions have doubled. Starting in 1970, they have doubled. So they were about 27, they are more than 50 in 2010. And from 2010 to now, there has been another increase. So we are not doing well. We are not taking care of this problem. And that is why 2015 is a milestone when almost all the governments in the world, not in Europe, in the world, they are saying this is a problem. We have to take action on that. But of course, actions have latency. So you cannot think that an action now has an immediate result, but still is important to take action as soon as possible. So what is the answer? We have now, I hope, a clear vision of the problems and on the potential solutions. And the answer is very simple. Use renewables energy sources, because we are not thinking of reducing a lot our energy consumption, because energy is beneficial to our community, is beneficial to health, is beneficial to wealth, is beneficial to mobility. So we are not thinking of zeroing the consumption of energy. This is very important. We are thinking of reducing the greenhouse gas emissions related to energy. And to do that, you need to use renewable energy sources and not non-renewable energy sources, as we are doing so far. So this picture is very important. You may say it is a dream. Maybe it is a dream, but it is a very important dream. Here is the forecast from now to 2050 of what should happen to stop the climate emergency. So very quickly, in black color, you have fossil fuels. So in 2012, we were using this amount of energy, and you see almost all of it is black. Only a tiny part is renewable. So this green tiny part at world level is the amount of energy produced by renewable. So what we should do, we should go to a level in 2050 where 100% of energy is produced by renewables. And there's more. A lot of energy is waste, meaning that, as an example, in many houses, we use an energy intensity very high. So you all know that there are houses where the amount of energy per square meter is low as 20 to 30 kilowatt per hour per square meters, or even less. But there are houses where the intensity of energy consumption is 500-600 kilowatt hour per square meters. So there are very different situations. And unfortunately, in our country, most of the buildings are in this class. But at the same time, we have the technology to build houses at less than 20 kilowatt per hour. So less than 1/20 of consumption. So this is an example of energy waste. And we have to solve this waste. How? There are many recipes, but the point is, if you look at this line, this is the BAU line, where BAU stands for business as usual. So basically, it means we are not doing nothing. So everything keeps the same. We keep our houses, we keep our cars, we keep our usage of industry, social habits, and so on. And what this does it mean? Without any action, the energy consumption will increase, and almost doubling from 12,000 to 20,000, almost doubling. But still, with action to reduce the energy waste, and these are this gray line, so these are reduction created by reduction from improved energy output by electricity over combustion and user efficiency. So this means that we already have the technology to implement these solutions. So end user efficiency means using better cars, using better houses, and net power demand reductions means using different technological solutions for our energy plants. And the problem is the gray part requires a lot of investment. So here there are $trillions of investments, because you need to change your house, you need to change the network of energy distribution, you need to change a lot of assets. But this is very important, because this action only reduces of a lot the energy consumed, and of course the corresponding greenhouse gas emissions. So this is action one. energy savings. So the gray usually is named energy savings. Then there are red, orange, blue, and light blue parts that are very straightforward. The green part is hydro and geothermal. Somebody was asking to me about geothermal. Here is geothermal. It's 0.67%. This is the maximum level. So it's important, but it's tiny in the overall picture. Then there is hydro. Hydro now is the green part. Hydro is 4%. We cannot increase it because we cannot have more waterfalls. We cannot create waterfalls. We have the waterfalls that are in the planet. So basically hydro is keeping constant, changing on the different seasons. So if it is a rainy season, you can have more. If it is not rainy, you have less. But this is the share of energy you can exploit, you can achieve from hydropower. Then there is red and orange, that is solar. And here you see huge potential amount. So this is the potential of solar energy you can have in the world. And what does the word potential mean? It means how large part of the world we can cover with solar panel without any significant impact on other things to produce this amount of energy. And this is huge. We can cover as high as 21% of energy by solar and about 15% of residential photovoltaics. Residential photovoltaics means photovoltaics on the rooftop of the houses, and utility means photovoltaics on industries and on grass, on lands. Then there is the blue part, blue and light blue, that is wind. And you see wind can cover as high as 23% in onshore, that means onshore, and offshore has a potential of 13.72%, and offshore means in the sea. So this is to say that this is the potential. So we can cover 100% of our energy demand by renewables, provided that we are using energy savings. So we are not increasing consumption with respect to 2012, using end-use efficiency and net power demand reduction. This is the solution, and this is the hard part to achieve. So, one last item in this picture, in 2050. So nobody is thinking that this revolution, because this is the highest revolution in humanity, the highest revolution in terms of social, economical, technological impact. You cannot think that this resolution will occur in 1 year or 2 years. It requires a lot of time because you require to change your houses. It is required to change all the networks. So as an example, natural gas will not be available. So you will not have natural gas in your house. So you need to use electrical energy to cool and to produce heat in your house. And so this is a very high revolution. Then, as an example, things about aircraft. How can you boost your aircraft without fuels, so without fossil fuels? How can you drive your ships? How can you drive your agricultural machines? So things are not trivial, and a number of years is required. At least 30 years are required for this transition. This is, of course, the transition we are all talking about. But one last comment. The transition cannot start in 2045. So you cannot just say, okay, we have 30 years, we will wait until 2045. This is false. The transitions means starting now, so that you can realize all the changes in networks, in social usage, in cultural usage, and then enable it with also political and economical drivers. So this is the solution, and some analysis of the solution. Some colleagues have made a feasibility study that you can retrieve here. And the feasibility study says, yes, you can move to 100% of renewable energy. Notice that biomass are not mentioned. So 100% means only wind, water, and sun, no biomass. And this is possible also in terms of social impact. Social impact would be huge. 27.7 million jobs will be lost. What does it mean? All the people working in the oil and gas industry will lose their jobs. And not only them, but all the related areas. But at the same time, the transition and the long-term maintenance of the new technology, so of solar panels, of solar production, installation, maintenance, wind, and so on, will create 52 million jobs. So still, we have a feasibility study that says that it is possible. But yes, think of being one of the 27.7 million families. It's not trivial. They are losing their job, they are losing years of experience and years of technology, ideas, and solutions. So this is a real revolution. Another picture, very important, is the price. So here is the price of energy, considering mortgage of investments and the overall cost of energy. So it is technical words, LCOE, levelized cost of energy, LCOE. So it includes not only the usage, but also the mortgage of investments and the depletion of the plants. So the overall cost. The black part is the actual cost, and the yellow part is the expected cost with renewables. It reduces, it is reduced by 42.5%. And why? Because you don't need fuels. So you don't need to extract fuels below Earth. So a lot of costs are reduced because sun, light, and water are available everywhere. So you don't need to use costly action to obtain primary energy. Primary energy is for free, is sunlight, is wind, is water. And of course, this is to say, yes, this is the solution, and yes, this is possible with the technology we have so far. So very important. This is possible with the technology we already have. It doesn't require any advance in technology or technological solutions. There is a question in the chat. Why don't they count on biomass? Second generation biofuel, for example, bioethanol from corn stover or rice straw can be potential sustainable sources or biofuel, right? I don't know. You place this answer. You have to try to investigate it. I'm usually I'm not stating yes or no. It's almost impossible to say yes or no in such a complex problem. So I will never give you final answers. I'm just trying you to be critical. So my answer is, this picture shows you that the potential is you can do without biomass. You can, because the potential is so that you can cover energy demand without biomass. And you are saying, and why cannot we use biomass? Well, the question is, I do not have an answer, only question. And what about competition between rice for food and energy? Would you like it? Would you like a price competition on crops used for producing food or for producing energy? Would it be nice? And at the same time, as I was saying before, this is from technical point of view very inefficient. So chlorophyll synthesis has an efficiency that is 10 to 100 less than photovoltaics. So basically, this is not an efficient way of using energy. So if you produce biofuel and use biofuel for your car, you are wasting a lot of energy in the process. If you're using electrolysis and hydrogen or better electrical energy, you have a much higher efficiency. So the question is, why should we make a competition between agro-energy, so crops used for producing energy, and crops for food? This is my point, but I repeat, no answers. This picture is just saying that you can do without biomass, but of course, these are edges. So the final destination will be a collective intelligence process. So don't forget of the problem of differences. So it would be very important to find a final point that is achieving the consensus, the agreement of every country. Another question, what about during winter? From the previous graph, 57% of energy if provided by solar that has a very low capacity factor. Are we going to use nuclear, no CO2 produced in combination or massive batteries, extremely expensive? Thanks. This is the good question. So this is potentially feasible, but there are some issues. Capacity factor and intermittence. We will talk about this problem in the next slides. So thanks for the questions. I will provide answers in the next slides. But yes, these are the real issues. Thanks for the question. We have the potential for producing energy, but using that is not so straightforward. So in one word, what does it mean, intermittence? With fossil fuel, you can switch on and off the plant when you need energy. So as an example, you can switch on and off at day and night, at any hour, according to the energy demand. With renewable, you cannot control the source. So you cannot ask for sun or more wind when you need energy. You can't do that. You will have the production, remember, conversion of energy when the weather decides. So the problem is capacity factor and intermittence. But I will show you how we can find solutions. You say extremely expensive batteries, not only extremely expensive batteries, but also batteries, of course. Another question, rice straw is a waste in rice production. That is the good point of second generation. It is not competitive. Yeah, I understand. So you're saying, okay, I want to use rice straw, not rice in competition with food, for production of biofuel. But once again, why should you use a technology that is less efficient than photovoltaics? So in the same crop, you could place a photovoltaic panel, and the amount of energy you obtain is much higher than producing rice and then rice straw and using rice straw to the biofuel process. So you understand the sequence of processes you require is very inefficient. So my question is, why should we use an inefficient process, even if it is not competitive with food? But this is not so straightforward. So I understand that you are using only rice straw, but you know, price driver are very dangerous. So what can ensure us that we are using only rice straw and not also the rice for biofuel, if there is economical driver leading us to prefer biofuel than other energy sources? So once again, I don't have recipes, I don't have final answers, just want you to think critically on the problem at large scale. And from the technological point of view, that is my expertise, I can say you that biofuel are much less efficient than other technologies. So I don't understand why should we use them. What about the great amount of carbon dioxide emissions linked to the extraction of what is necessary to build tools for a green turn? For instance, rare earth elements for solar panel. And which rare earth elements you need for solar panel? This is the real question. So when you think of this problem, which is a real problem, so the question is, but try to be honest. What is the cost of the transition? How many material you require to produce panels? How many minerals you require to produce wind farms? Yes, these are problems, but you must see this problem in comparison with fossil fuel. So what is the amount of minerals and of energy you require for oil extraction? What is the amount of energy and minerals you require for natural gas extraction? So this is the real assessment you have to do. And of course, the green turn must be better than before. So as an example, we can do photovoltaics without rare air elements, and we must do that. So the answer is, this is an issue. We have to take care of it, but remember that the final answer is not 0, is better than before. So we are replacing oil extraction. So the point is, how much is the impact of oil extraction? And we will see in the next slide some benchmarks. So I will show you how you can assess exactly this impact. And the benchmark is named ERO-EIO, which is the energy return on energy invested. So basically, the way to provide a clear assessment on your question is, what is the ratio between the energy you produce in your lifetime and what is the energy you require to build the device? So there is a energy return on energy invested for oil, and there is an energy return on energy investment for panels, for solar panels and for wind turbine and so on. So we will see some benchmark on that. So it's 4:45. Thanks for all your very interesting questions. I hope I'm providing you some, not answers, as I said, but some critical thoughts, food for thoughts. And I will take some break. So it's 4:45. We will now stop until 4:55, so 10 minutes break. So we are restarting our lecture. And we will go deeply into renewables and also answering some of your questions on the problems of renewables in comparison to fossil fuels. So just a reminder, renewables stands for primary energy, so a natural resource or source of energy that is not depleted by use. And we are referring specifically to water, wind, or solar, not to biomass. But we have already discussed on biomass. This can be considered renewable. However, it is not so quick. So the regeneration requires some year, so the year of the plant production. Currently, renewables, this is a picture of the IEA, the International Energy Agency. Currently, the share of global electricity generation in 2018 is 26%. So in 2018, 26% of electricity was generated by renewables. Last Monday, some of you reminded us that in 2020, there was the overcome. So renewables has overcome fossil fuels in global electricity generation. So something is moving, but still very far away from 100%. So I will try to provide you some basic description on the single technologies. So we will briefly introducing, of course, from a qualitative point of view, technologies for water that are named tidal, so energy from sea waves, and hydro, and of course wind, and third, solar, that can be broadly classified into three types: photovoltaics, concentrating solar, and thermal panels. So as I said before, in order to assess the different technologies, considering as an example the problem of natural resources to build devices, we will use a benchmark, actually two benchmarks. One is LCA, which stands for life cycle assessment. So it's very important to compare technologies during all their lifetime. As an example, some of you have mentioned nuclear energy. What is the problem of nuclear energy? Is decommissioning. So decommissioning for nuclear plant may require 20 to 30,000 years. So, of course, when computing the decommissioning of a nuclear plant, numbers are blowing up. And so, of course, if you want to make an honest comparison, you always see that nuclear is not competitive with the others. So one benchmark is a method named LCA, standing for the lifetime analysis. So even the hidden parts are considered. You might remember last Monday, I was saying that in a car, 25% of energy is consumed for manufacturing. So this is the construction part that is important. and as was asked before, may require precious minerals or rare materials. We are trying to assess it with the second benchmark, that is EROEI. That is an objective index that is basically defined as energy returned on energy invested. Energy returned on energy invested. So it is the ratio between the blue part, so cumulated energy production, and all the red part. And of course, what is important is net energy. So ERO-E larger than 1 means that during the lifetime, you have produced an amount of energy higher than what is required for construction and decommissioning. And of course, you see here a red part even during lifetime, because of course there are losses. So not all the energy is used, there are losses. As an example, there might be self-consumptions. So you might require some part of energy for the system itself. As an example, if you are using a wind turbine, you will move the turbine to follow the wind, and you require energy to move the turbine. And this is self-consumption. So this doesn't contribute to the energy to the consumer. This is self-consumption. And of course, you might have losses that are the losses of transformation. So there are parts in the system that produce heat, and this is not net energy to the consumer. So I hope you now have a clear picture of what is energy returned on energy invested, and I will show you some benchmarks also to answer the previous questions. So these are pictures of energy returned on energy invested for several technologies. So you see that in general, numbers are quite low. So for both natural gas, coal, and nuclear, the energy returned on energy invested is quite low, is around 5-10. So meaning that you consume 1 unit of energy for decommissioning and construction, self-consumption and losses. And with respect to that unity, you have 10 times more energy to the consumer, net energy to the consumer. And you see that the most interesting technology is hydro. Hydro is quite simple. You have only turbine and then electric machine for conversion of mechanical energy into electrical energy. We have seen it last Monday. And its energy return on energy invested can be easily larger than 80. Huge energy return in energy invested. Also because this technology duration is very high. I already said that the energy plant installed by Tesla at Niagara Falls is still there after about 2 centuries. So you may understand the lifetime of this technology is very high. And of course, as was said before, everybody pays a lot of attention to the last 2 parts. So wind and solar. So wind is very appealing because it's after hydro, the most effective technology. Then there is solar, and solar is not so good as the previous question was asking. There are many hidden parts for minerals, for other materials required for the device, so for the panel. And this is computed here. So the energy returned on energy invested for solar panel is ranging from 4 to 5 to 10. This is typical numbers. But here there is a comment which is very important. In a recent paper, it was mentioned that this number is an average. So this 10, 8, 12 energy returned on energy invested for photovoltaics, meaning that 1 is the unit of energy required for construction, self-consumption, and decommissioning, and 12, 10 times more is the energy produced for the consumer. This number is quite controversial. You can find papers or reports stating that it ranges from 2.7 to 30. So huge variance. Because there is a large spread of data and technology. So basically what we are saying here, we have installation related to different technologies. So installation related to panel installed in 1970, still working, and panels installed in 2010. So there is a wide gap of technologies, and this paper is stating that recent technology are performing much better. So you basically, as an example, can try to avoid rare earth material. So the discussion is still happening. You would say, I don't see oil here. Well, the reason for that is the same for photovoltaics. Numbers for oil are really diverse. You have oil extracted in Saudi Arabia until the 90s of last centuries, and you would see that the energy return on energy invested for oil in Saudi Arabia is around 100, because the oil is almost at earth level and it's very easy to extract it. At the same time, you have oil extracted in North Pole, where you go deep in the sea, in the North Pole, with very complex technology, and the energy return on energy invested for that oil is much lower than 10. At the same time, you have shale gas, which is another fossil fuel recently discovered, where the energy return on energy invested is very low. So I'm not placing number for oil, not me, but the paper I'm using here, because it's very diverse. But still, looking at trends, we have a trend for oil that is decreasing its energy return on energy invested. And it is decreasing because it's harder to find it. At the same time, when it comes to solar or wind, you have better technologies, so the energy return on energy invested is improving. So conclusion is, as an expert, as a scientist, as a technician, you have to know the methods. And the methods I'm providing you, use LCA and ERO-E to make your choices. This is the best recipe I can provide to you. And these are, as I said, numbers for oil. And another important picture on the right, we were talking about raw materials. We were talking about rare earth for photovoltaics, but in general, we must be aware that the problem of raw material is a huge problem. It's a huge problem because we are living in a spaceship where when a specific element is depleted, we don't have any more. When a specific species in the biodiversity is erased, is extincted, we don't have it anymore. So in terms of resources, numbers are impressive. In 1990, we were extracting 50 billion of tons of raw material. 50 billions of tons. Try to guess how large is this amount of material we are extracting from the earth every year. In 2050, we are extracting more, 70 billion of tons of raw material, meaning 27 kilograms per capita per day. Every day, each of us is extracting from the earth 27 kilograms of material. So this is not a comics, this is reality, meaning that, as it happens for oil, in 1919 you can find material easily. Now you have to go deep to find the same material. And this is not comics, because the picture behind, you don't see it, is an open copper mine. So they are extracting copper, and you can easily see that they are extracting copper at open air at 1,000 meters deep. So the depth of the mining is now more than 1,000 meters, and it was 10 meters just 30 or 40 years ago, because copper is precious. You require copper for any kind of power lines, or for your smartphones, or for everything you use with electrical energy. And so copper is reducing. So as a general picture, I guess many of you know the table of chemical elements. This is the classical table of chemical elements, order in terms of atomic weight. So hydrogen is 1 because its atomic weight is 1, and then it increases. But you see here a strange shape. What does it mean? So here we are making large chemical elements for hydrogen or nitrogen or oxygen, because we have plenty of that. So large shape and green color means we have full availability. At the same time, we have yellow part, meaning there are some hazard. You can have or not have it in the future. But we have also orange, like uranium, meaning that nuclear energy is not so straightforward, because it requires raw materials that are rare, like uranium. So it might be limited in the future. But the terrible part of this picture is that we have also red color, meaning materials that will be unavailable in 100 years. So in 100 years, we might not have enough of that materials. So you see many materials that are used for smartphones. So this icon means smartphone, and many of the red materials are used for smartphone and for other technologies. As an example, for solar panels, some of them, the rare earth materials that were mentioned before. So the bottom line of this picture is we must be careful. You cannot only solve one issue, the issue of energy, if you don't take care to chemical elements, to raw materials. So it's very important to consider both problems. So it's true that we have to take care of the material we are using for the green turn, but still we are already depleting materials without the green turn. So things are not black or white, but we have to have clear methods and awareness. And this picture that is provided by European Chemical Society, I guess you can find it in different languages. Here it is Italian, sorry. Is very clear and very scary at the same time, and remind us that when some materials is over, we don't have it anymore. We need to go to Mars. And just kidding, of course, but not so kidding, because we will not have it anymore. I go back to copper. There is a typical story on copper. Roughly, you can say that 1/3 of copper is on power lines. So you know that all around the world there are power lines. Power lines and all the other appliances use 1/3 of the overall copper you have in the world. 1/3 is in the earth, so it's still to be mined. And you know where is the third? You have some guess for the third? It's in landfill. It's in landfill. 1/3 of the overall copper that is named red gold is in landfill. So when you go to lower income country, you will find kids go in landfill and look within the landfill for gold, for silver, for copper, because in landfill there are a lot of this precious material. And this is what we should not repeat. So you must be aware that the energy transition is totally in agreement with the so-called circular economy. So you cannot do things without being very, very careful about decommissioning. So when you produce solar panel, the question before, you must be aware that if you are using rare earth elements, they must be recycled. So their lifetime must be forever. This is the only conclusion I want to share with you. So we are starting a transition. We shall not repeat the errors of the past. So don't use landfill for materials. Somebody is saying, and estimation is probably right, that in a landfill in Japan, you can find up to 50 million tons of gold. Why? Because in every devices you are just throwing away, there is gold for connections. There is silver for connection. There is rare materials. So we shall not forget that throwing away things is not so advisable as could be, because it is a problem in terms of sustainability. It is a problem of having forever such possibility and such materials. So after this important analysis on benchmarks and on raw materials, I moved to technology. So water, wind, and sunlight. What are the main technologies we have for conversion of energy from water? So from water, we have two technologies. Top is hydro. Bottom is tidal. So tidal means a turbine. This is the turbine placed below the water. So the waves, the sea waves, makes the turbine spin, and the mechanical energy created by the spinning of the wheel is converted to electrical energy. So quite simple concept and quite simple technology. You remember hydro as the highest energy returned on energy invested, and of course tidal also. You basically require a turbine. A turbine is this. So it's a set of metal with specific form to provide the better conversion of fluid movement to mechanical spinning. And then the same technology is on hydro, where the mechanical speed, the mechanical spinning, is produced by a waterfall. So the waterfall produces pressure to a turbine. So in tidal, the pressure on sea waves is created by nature, and hydro is created by waterfall. And then, of course, as we have seen last Monday, the mechanical energy created by the turbine is converted to electrical energy, but by an electric generator. And then it provides electrical energy to our power lines. These are the power lines for tidal, and these are the power lines for hydro. A very important feature of this renewable energy sources is that it can be controlled. So you can decide when to switch it on and when to switch it off, because basically you can move the turbine and decide whether you want to convert the energy or not. And also another wonderful feature of hydro, not tidal, is that it can be used as an energy storage. So you probably know that Italy has a large amount of energy storage, typically electrical energy storage. Typically, France has a surplus of energy at some moments, typically at night, because they have a lot of nuclear plants, and the nuclear plants cannot be switched off and on when you want, because to switch on and off a nuclear plant, you have many safety issues. So you cannot just decide to switch on and off the nuclear fission. So because there are temperature and magnetic issues, so it's not something you can easily control. So basically they have a lot of surplus of energy. What does it mean, surplus of energy? It means that you are producing more energy than your demand. And this typically happens at night when the industry are not working fully and the cities are over, so you don't have lights and whatever. So at night time, France typically has a surplus of energy. What does it mean? The price of energy goes down to zero because nobody wants it, so you can only just throw it away, burning it. So Italy, on the other hand, has a wide capacity of storage. So usually Italy buys electricity at night from France and then store it some way, like a battery or an hard disk, is store it. And then it reuse it when during the day it requires it. So it's very interesting. You buy it at low price and you use it when you like it. This was the main way of revenues of Enel, of Italian energy company, national energy company. So how does it work? And why we have so many capacity of storage? Because we are using hydro. Hydro can be a storage for electric energy. Sorry, can store electric energy. And how? Very simple. When you have a surplus of energy, you raise the water. So you raise the water with a pump and you use the electrical energy to supply the pump that raise the water. Then when you want to reuse the energy stored, you just leave the water and the water falls, enables the turbine, and you use the electric generator as an electric generator. Pretty simple. Almost all hydro plants in Italy have this feature. So they can be used in both directions, producing energy and storing water to store electricity. And that's why we have this capacity of being a reservoir for those countries that have a surplus of energy. As an example, France for nuclear energy. So this is water. Very, very interesting. Probably tiny. We have seen it before as a forecast, quite tiny, 4%, but very interesting for these two reasons. It can be controlled and it also can be used for storage. So very, very important technology, water. Then we have wind. I guess you know about wind. We have two different technologies. One is wind farm with horizontal axis. That is this typical installation where the nacelle, this thing here is called nacelle, moves to follow the wind direction. So you can move it. Of course, it's controlled by an electric system to follow the direction of the wind. Then there is the turbine that moves. You have to remember that this is incredible. So the nacelle is as large as a bus. So here you should think of a bus car, a bus vehicle, and the turbine can be as high as 50 meters. And the single blade is around 30 meters. So we see it very far, but it's really huge system. And it can produce as high as 10 megawatt. So 10 million watt for each wind turbine. And this is horizontal axis technology. Then we have less known, but very important, vertical axis. Vertical axis means that it spins vertically. So the main difference is it doesn't require to be aligned. So you don't require any control. It spins every time in any direction of the wind. So it's very interesting. And also it's also less noisy. So you see here, this is an installation in a school. So this is a school, and you can use this wind turbine very simply integrated in the standard environment. So vertical axis turbine are not known here because we do not have wind. So the main difference between us and UK or Denmark or North Europe is that we have a low intensity of wind, because in order to have the right energy return on energy invested, you need wind, because otherwise it doesn't make sense. And here, the amount of wind, meaning the number of hours of wind in average in the year, is not interesting unless in the sea. Of course, the sea, in the sea, the wind level is higher, and also wind intensity. And of course, if you go height, so if you go in the mountain, you have higher wind and higher wind intensity during the year. But still, this is very interesting technology. The only issue is that the size of this plant is much lower. So it goes up to some 10th of watt, not more. So is different things. It's competitive with solar panel. So sorry, I forgot a K. K stands for 1,000. So 10 to 1,000 to 10,000 to 100,000 watt, which is about 1, 2, 3 order of magnitude less than that. So it's interesting for several reasons, specifically for noise compatibility, but it's much, the size is much lower than before. We have a question on water. Sorry, how many watt can produce vertical wind turbine? I guess I already placed the answer here. Second question about the water. The construction of dams has serious consequences on river ecosystem. It would be also important to consider the environmental impact. Yes, and that's why we are not increasing it. So if you look at the forecast, we are saying we are not increasing it. So we all know that the dams have a wide impact. So we are not thinking of increasing the number of dams. We are just limiting it to what is feasible for the environment. So the problem is that you are reducing the river flow. So the energy conservation is for everything. So if you place a dam, you are reducing the energy available to the river. So with all the consequences that comes to the fishing ecosystem, to the general ecosystem. So of course, this is true. And that's why we are not increasing its number and its impact. Another question, I've heard that there is a global challenge to share electrical energy in excess that cannot be stored between states through a global network. Do you think that will be possible and useful? Yes, but there are some limitations. The limitation is that you cannot easily exchange energy at very long distances. So it works in neighborhood. So it can be helpful, as an example, in a part of a city. So let's say that I have an excess of energy now, because I have a photovoltaics and your house is close to me, we can exchange energy within neighborhood. But at larger distance, there are many issues, mainly caused by the distribution network. So the distribution network is still not ready for this kind of exchanges, and this limits this global sharing. But yes, sharing and storage and the so-called smart network is one of the open issues that we have, as was asked before, and still I didn't answer to the problem on intermittence. I will do it in a moment. And so another short comment on wind turbine. We have all the technologies. So we are now capable of converting energy better than nature does. So we have very strong capability. So here, I will not delve into detail, but this is one of the top capability of engineering. So here you have mechanical engineering, electrical engineering, electronic engineering, chemical engineering, civil engineering. It's really the top of performances we have, and really it is a wonderful technology with impact. We do not never say zero impact. It's not true. We are placing it in nature. We are using soil. We are preventing bird flow. So we are having a large impact with such an installation. But once again, you have to compare it with other solutions, and with effective methods, decide for the best. This is the only thing I can say you. And I repeat, we have the technology. So the technology for that is really one of the best that engineering can provide to you. Then the last part is solar. I guess you all know about solar, but you probably do not know that there are many flavors. So there are many different technologies. CIS stands for small films. So means that you can make the shape you want. So you can use this flat, thin panel for, I don't know, a window, a car, whatever shape you want. It's totally flexible. Then we have another technology that is usually called polycrystalline or monocrystalline, that are different technologies. I will not delve into detail. I will just say to you that these are performances. So the yellow line stands for how many square meter you require to produce 1 kilowatt. So to produce 1 kilowatt with this technology, you require only 5 square meter. With this one, 8, and with this one, 16. So 3 times more than 3 times more. But this one is this one. So it is less efficient, but more flexible. So this is just to say, we do not have only one solution. We have many solutions. So going back to rare earth material, not all of them have rare earth material. There are really very different solutions. So once again, in terms of efficiency, of course, it's the other way around. So this has the higher efficiency. So 20% of the solar energy is converting to electricity. Photosynthesis, chlorophyll and photosynthesis has less than 0.2%. So this is just to say we are performing much better than nature. And we have so many different solutions. And sorry. these are other specific examples. So flat film, monocrystalline, and polycrystalline. These are the same as before, just to make you picture, to recognize them. So monocrystalline is very, very simple structure. Polycrystalline is heterogeneous, and amorphous flat film is flat, is flexible. And these are another way of seeing the same. So how large is the space required for 1 kilowatt? And you can see here that with monocrystalline, you have the same power, 1 kilowatt, with small size, but with amorphous, that is flexible, you have larger size, but different feature. And this is the trend. So this is the history of solar performances. So you see that we have technologies as high as 48. So we can go in labs and have prototypes going up to 48, which is incredible. So about 1/2 of the solar energy is converted into electricity. So basically, think about it. If you go there, there is no more sun. So it's totally erased the energy of the sun on the earth. So it's almost incredible. As high as you can completely convert solar energy into electrical, which is even impressive. But at the same time, you see that there is a larger trend of technology. So every kind of technology, the colors states the different technology. So this is the pink one is multi-junction, so different technologies together. The blue one is the crystalline we were saying before, and this orange is quite interesting for the question was placed before, because these are organic. So these are technologies based on organic materials. So of course, you don't have the performances of the others, but still they have around 10%, which is much better than chlorophyll and photosynthesis. So this is just to say technologies is evolving, and we have many different solutions for every application. So as an example, we could think of some solutions for wind, for window, for car window. We can think of solutions for dresses, for coat. So to recharge our batteries or our devices. So everything is open to technologies, and we have all the solutions. We just need to decide how to use them. And this was solar. For solar, I remember that the technology is based on the photovoltaic effect. This was discovered by Becquerel about some more of a century ago. And it is incredible that about 20% or more of energy can be converted into electricity. So basically, photons are converted directly into electrons. And this is the magician, which is not magic, but it's science behind this process that works very well. And of course, how can we go as high as 50%? Because we are merging different technologies. So multi-junction means using different materials. Each of them use different wavelengths of photons. And so using them together, you go as high as 50% of conversion in energy, which is really amazing. And solar is not only photovoltaics. Solar is also thermal power. You remember last Monday, we have seen that every energy plant is basically made of 3 steps: heat, heat converted to mechanical energy by a steam engine, and then mechanical energy converted into electricity by an electric generator. So 3 different processes, 3 different cells in the matrix of energy conversion. So how can we produce electrical energy from heat? So the idea is to have very high level of heat. So very high means higher than 500 Celsius, 1000 Celsius. This is the minimum level of temperature you shall achieve to enable the steam engine. So these are the solutions. Power tower, where you concentrate, these are glasses that concentrate the heat in a single point. So you are focusing all the sun in the same point, and of course here there is water. It's not water, but it's a fluid that is brought to very high temperature. And this temperature of the fluid is used for a steam engine, and then to convert mechanical power from the steam engine to electricity. Parabolic through is the same idea. You are focusing energy here, and you have very high temperature for the fluid here. And then this fluid is used for a steam engine and then for electricity generator. And the same concept is here. Here you have the device where the high temperature is concentrated, and then you can use it. Of course, these solutions are installed. They are not prototypes, they are real installation, but they are installed in the deserts because you need very high sun to mortgage the investment, and also you need very high number of solar hours, of sun hours per year. So these are examples in Nevada or in Spain. And currently there are more than 3 gigawatt of installation foreseen. Very edge technologies, but it works. So it can be used in some locations, not everywhere, for electrical energy production. But still, as was said before, not every time. So you cannot decide to switch it on or off because the sun decided, not you. So during nighttime, the electricity produced is 0 because you don't have sun that enables the process of energy production. And of course, the nice thing is that you can use photovoltaics or even solar thermal. We have solar thermal devices for rooftops quite easily in our installation. So we were talking about dams before. Here we have the same problem. If we are using land to install new panels, this is not very good solution because of course the panel uses the energy of the sun, so you do not have sun energy for the crop. So you are placing an impact to the ecosystem, not as high as a dam, but it is an impact. So of course would be preferable to use existing urban areas, and we have many existing urban areas. So it's very easy to use photovoltaics in existing land use. So without reducing the land use for agriculture or for nature. That is very, very important aspect I want to address. So once again, it's 5:50, and I will stop now for another 10-minute break. And the last part would be on the answer to the question on intermittence. So yes, we have seen many technologies. We have seen that we have the solutions, but we have also problems. Problems for manufacturing, problems for materials, but most of that problems for the use. Renewables are intermittent, so you cannot switch it on and off. So I will try in this last part to show you how we can manage the problem of intermittence, trying to provide solutions for energy storage, for more flexible use of renewables. So a last break, and we will start again around 6 p.m. So here we are, we start the last part of the lecture and the last part of this specific topic on climate and energy. So the point is renewable are available, but it's not easy to embed them in our energy system. The reason for that is quite technical, so I will try to be as simple as possible to explain you why it's not so easy to embed, to integrate renewables in our electrical system. So the electrical system can be thought as a river. So electricity is like a river, let's say a closed river. So there are some sources providing water to the river, and there are many users receiving water from the river. And of course, the level of the river must be kept constant, instantaneously, as I said last Monday. Because if you are using much water than the sources provide, the river goes to zero level. But on the other hand, if you are providing sources much more than the users demand, you are flooding the river. You are producing floods. So this is a perfect equilibrium that must be kept instantaneously. So in traditional energy system, that is the energy system we have so far, we have a centralized energy system. What does it mean? It means that we have a small number of sources, few sources, few and huge. So each energy source is producing about 1 gigawatt. So these are, of course, average numbers, typical numbers, but this is to say a general picture. So you have small sources of 1 gigawatt. Users are typically 3 kilowatt, which is the size of an house. So you see there is about 1 million of difference. So you have about 1,200,000 users for one plant. So one plant, 1 million users. So this is the centralized energy system, which is the system we have so far. In my hometown, we do not have no power plants because the power plants are in other cities and they are providing energy for a lot of cities. So this is a very centralized system. And there are technologies, but I will not delve into detail for that. But the problem is that this system is not reversible. So basically, the flow is flowing on one direction. The flow of energy is coming this direction and this direction. So it's coming from the sources and to the users. It's not reversible. So you cannot go the other way. So it's not easy to do that. And this is a technical reason, because the devices that are in these pictures are not reversible. So you cannot use them in both directions of energy. And this is the problem for renewables, because when you have a mixed system, you have, as an example, solar panel in the houses, and you have large plants and small plants, because the wind turbine, we said it before, is around 10 megawatt. So it's small, and there are large plants. So it's an hybrid system. You have both centralized, and you have distributed. Distributed means you have many different small sources. As an example, a photovoltaic in a rooftop has about 1 to 5 kilowatt. So very small, but distributed. So many sources. But the house is producing, but using energy at the same time. So it's a so-called prosumer. Prosumer stands for producer and consumer. So this is a prosumer. Prosumer, because you are doing both action at the same time. So in your house, you are producing energy with your solar panel, but you are also using the energy coming from the power lines. And why? Because there is a time difference between production and use. So as an example, you are producing a lot of energy at daytime, but you might need energy at night for your appliances. So for your washing machine. And at night, you do not have energy produced by the photovoltaics. So you need also the power lines to cover the time difference between production and use. But at the same time, when the photovoltaics is working, as an example, at noon, and nobody is at home, and the washing machine is not working, probably there is a surplus of energy. So you are producing more energy than what is required in the house. So you are a producer. You are selling the energy to the network. So you are doing what is forbidden. So you are doing the yellow line, the green line, the green arrow. So you are trying to send energy back to the river. You're trying to send back water to the river, sticking to the example. But it's the same thing. So is the river ready to get energy from you? Not yet. Not yet. So basically, there is an economical agreement. They are paying for you, but this energy is not actually used. Not of all is actually used, because many devices cannot be used in both directions. So as an example, you can use it locally. So in your neighborhood, as I said before, so my surplus of energy can be used by neighborhoods, but not by other cities. So it is quite complex. And I do not have time, and more than this, you do not have knowledge for going deep into it. But I'm trying to be clear at qualitative level. So the problem is renewable has two main problems. One is intermittence. So you cannot switch it on and off when you need the energy. So there is a time difference between production and use. Second, the energy is not suited to the distribution network. So the distribution network is not ready for prosumer. And we have to solve both problems. And how? Many different solutions. We do not have recipes. We need to create a revolution. And the recipes is use very different solutions in many different parts. So one solution is storage. So you could install a storage in your house, meaning that, for example, a battery, meaning that you produce a lot of energy at noon, nobody's at home, you store the energy in the battery, and then you release it at night time for your washing machines or other appliances. And this is local storage. But you also need system storage. So as an example, a storage here to store the energy of different small users, of different small prosumers, and then reuse it in the river. So basically we're saying the river has changed. It requires new things, storage at local level and intermediate storage to provide a distributed system that can work with different levels. Of course, this is the major problem, the major system hindering the transition, because it requires investments and it requires changes in the power lines and in the energy system that is all around the world and requires huge and massive investments. Somebody of you said batteries are expensive. Yes, batteries are expensive, but we could think of intermediate solution. As an example, you could use your electric vehicle battery. So you could use your car, provided that it is an electric vehicle that has a battery, very large battery, for storage, using and storing the energy in some conditions. But this requires many social actions. As an example, we should realize a system, as was said before, with a share of energy excess. So we must be ready for laws and for social implications of sharing energy between others. So it's not an individual system, it's a shared system. At the same time, we should be used to sharing cars. So it's not easy to have such a model with individual devices, but it's quite possible with sharing methods. And more specifically, the concept is here. So renewables can be viable provided that you have technologies to store energy up to 4 or 5 hours. So provided that you can store the energy you produce by renewables by 4 or 5 hours, you have the capability of realizing the so-called electrical energy time shift. It means that you can produce electrical energy at noon and reuse it at 6 p.m. So when there is no more sun and your photovoltaics is not producing, this is electrical energy time shift. And this kind of storage exists, and it's not only batteries. There are mechanical storage, and there are many different solutions coming to market of mechanical storage, and there is water storage. Water storage is what I already have given to you with the example of hydro. This is water storage. And there is also mechanical storage. Mechanical storage means converting the energy in surplus, so the energy at noon you're not using, to mechanical flywheel, spinning, just spinning with very low friction. And this is mechanical storage. There are many, many different solutions. Somebody is also thinking of using underground. So going underground with a very heavy weight and raise it when you have excess of energy and release it when you want to store the energy. So there are really many different solutions. Many of them are already installed at intermediate level. So many of these mechanical or chemical solutions for storage are already installed here. So at intermediate level, at level of cities or at level of plants, but we have to change the energy system. So we have to move from the current centralized electrical energy system to smart grids. And this will be the enabling technology. So smart grid and energy storage are the enabling technology for renewable. And this is the missing piece. This is the investment we have to do now that will enable the transition to renewable. I'm always surprised that almost nobody talk about it. So you always heard of transition, you always heard of renewables, but probably hardly ever on smart grid. But this is the real missing pieces. It's the enabling technology that would allow the real transition to renewable, but because then you can use your house as a prosumer and you can use renewable everywhere and switch from current fossil fuel-based energy system to renewable-based energy system. Technologies are viable, but we need social and technological change based on smart grids. And so this is an example, as I said before, typical production from photovoltaics. This is ours, so this is day 1. And this is day 2. And the blue line is the instantaneous power production. So of course, the same device in your rooftop provides up to 2.4 kilowatt. So this is kilowatt in left vertical axis. So you have a peak production of 2.4 kilowatt, but only at noon. Before that, you have less than that in a parabolic waveform. Then, of course, is day 2, is the same, we assume the same climate, same weather. So it's similar. You have a peak production of 2.4 kilowatt of energy converted to electricity from the sun, but only at noon. And the red one is the cumulative energy. So provided that you can store this energy, in 2 days, you go up to 35 kilowatt per hour. The red lines is kilowatt per hour. So 1 kilowatt produced during 1 hour is 1 kilowatt per hour, meaning that 1 kilowatt per hour is 0.2 euro. This is the economic value. This is what you pay, the bill you pay to the energy provider. So basically, if you could store this energy, it doesn't, it's not wasted. It is up to 35 kilowatt per hour, which is huge amount of energy. It could cover about all the energy demand of your house. It covers the washing machine, it covers the refrigerator and all the appliances you have in 2 days, but you need storage. And this is the enabling technology, the missing part that will enable the transition to renewables. So to answer the question, we have the technologies. It's not only chemical that is costly, but more than that, it uses very precious materials and rare materials, we probably do not have enough lithium, as we have seen before, to cover the demand of battery for all the world, but we can use alternative solution like water and mechanical. So an hybrid system is possible, and once again, we have to design this transition, the missing part. So I pretty much I have concluded my lectures. So like we said at the end of the last lecture, I used the right pace. So the last part is just a test for you, is food for thought. So my suggestion to you is to test yourself. So how do you assess yourself? Are you performing well? Are you having a good relationship with the earth and with the nature or not? How can you say that? There is a test which is very effective and very simple. You can do it now, that will compute your ecological footprint. So before letting you play with the test, I will try to explain you the ecological footprint in 2 minutes. What is the ecological footprint? Is the space you use in the earth. Well, I know the space I use in the earth, it's myself. No, it's not true. You're using much more space. And how you can assess the space you occupy? Well, basically, in 1997, some researchers defined the ecological footprint. They are Walker-Nagel and Rees. Their idea was very, very nice, still used. So economics from an ecological footprint perspective. So let's define the space occupied by a city. What is the space occupied by a city? Well, this picture tells you everything. The space occupied by a city is not the real soil, the real land use. Is the space that the city uses in terms of crops to provide foods for the inhabitants, in terms of raw material to provide energy and resources like cars or cement or steel for their inhabitants, and is also the space you require for waste, because this inhabitant, by economic system, use space to produce resources and then require space to landfill, to deplete the material you're not using anymore. And this is the ecological footprint. So the space is not this one, is much larger. Okay? You understand the ecological footprint? So you understand that we are using a space that is much larger than real space. And there is now a public system, not public, but available to everybody, that is the Global Footprint Network. So you can easily retrieve on the web the Global Footprint Network that is, of course, was funded by Walker-Nagel. And basically they are assessing two different measure units. They are measuring ecological footprint and biocapacity. Ecological footprint is the space used from the inhabitant of a given country. So the red line is the space used by Italians. So ecological footprint is the space used by all the Italians from 1961 to 2013. So you see that we are increasing the space we are using. So we were using about 2.5 units of space. We are now using 4.5. So our ecological footprint has almost doubled. The green line that is less than 1 unit is the space available. So in Italy, in the overall country land, we have about 1, and we are using 2.5. And how is it possible? Well, in the bottom chart, there is the case of Congo. In Congo, they have 10 biocapacity in 2013, and they are using 0.1. So the inhabitants are using much less resources than they had. And please be aware that this 10.78 was about 48 in 1961. So guess what is happening? Sorry, what has happened since 1961 to nowadays? You know the answer? We are exploiting these resources. We, and we means I, you, your colleague, my colleague professors, because Congo is one of the reservoir or main raw materials like diamonds, steel, coltan, all the material we are using in our life, in our society. So the answer is yes, is exactly what you are guessing. We are depleting materials from others. And then there is another important point. This biocapacity is referring to instantaneous biocapacity. So we are not accounting here from resources from the past. So when you are using fossil fuel, you can use more than the biocapacity you have because you are using biocapacity of the past. So in simple words, let's assume my income is 1,000 euro per month. Can I spend 2,000 euro per month? Yes. If I have capital in the bank, I can do that. But the question is, how long can you spend 2,000 if your income is 1,000? And this is the same point. We are spending 2.5 times more than we have, and we can do it because we are reducing the capital, the natural capital of the earth. How long we can do that? This is the question I leave you as a conclusion for my lecture. And as a conclusion for you, please test yourself. Test yourself and you will see how many earth you require. Typically in Italy, we are using 2.5 earth, 2.5 earth, because we are using resources from the past and we are using more resources than we have on our own country. But test yourself. You won't be surprised if your answer is 4. It depends on you, on your lifestyle, on your impact on the different patterns of biocapacity. Please do so. It's very interesting. Thank you. This is the last part of my lecture. So I leave the floor to Alberto for conclusion and then to open for next lectures.
Okay, thank you. I wonder whether all the questions in the chat were addressed. Let me just, because I think, I'm not sure.
Yes, all the ones I've seen, I've received an answer.
Okay, very good. Thank you.
But of course, if there are other questions, I'm happy to discuss them.
Okay, very good. Thanks a lot, Alberto, for this these interesting 6 hours of lectures. Indeed, I think you covered a topic that is extremely important for providing the context of the science of climate change and climate actions, and in particular climate actions. Of course, they are strictly related to energy. And I think your slides are already available. Not I think, I'm sure they are already available on Virtuale. So I just would like to remind the students the plan for the next lectures. The next one will be in 2 weeks from now, because next Monday is Easter Monday. And the next lecture will be delivered by Professor Alessandro Gargini. It will be April 12. And then we will have, before the last lecture, a break of 3 weeks. The course is going to be closed by me with the final lecture on May 3rd. So this is our plan. And in the last 2 lectures, we will also give information on the exam. And we aim also to provide a test quiz where you can test yourself with respect to questions that are similar to those that you will find at the exam. But we will give more details during the next lecture and of course the last one. And at the next lecture, we can also give details on the exam dates, which will be fixed after June 7, because we can start making exams from June 7. That's it. I wonder whether you students want to take the opportunity to ask any question now on the chat. And of course, the chat in Teams will remain available for you if you have any further question. And as you have seen, the chat in Teams is also a channel that sometimes we use to give you some suggested readings. So any questions, students, from your side? Okay, it seems that there are no questions. So I would like to thank Professor Bellini for the lecture, Francesco and Giacomo for the simultaneous translation. And of course, I'm very also pleased to thank you, students, for your attendance. And again, if you have any question or suggestions, please feel free to use the chat in Teams. So goodbye and enjoy your Easter break. Let's take some relax as much as we can. Of course, the situation it's characterized by several constraints, but still, let's try to enjoy this break in the best way we can. Thank you very much. Grazie Alberto ancora una volta. Thanks to everybody. Bye bye.
Grazie, arrivederci.
Grazie, arrivederci.